some exterior calculus.
Okay, so thanks very much for the invitation to speak, and thanks very much for putting 2 talks before my talk, which mean that I can go through the first few slides very quickly, which should give me something of an advantage. Okay, so this work, like the work that John talked about, is part of this gung-ho dynamical core project that's trying to look at developing a new dynamical core for the UK Met Office. It's kind of a big collaboration that we have. And most of my work is in the grids work package, and the aim of the grids work package is, as John described, to find some numerical discretizations in the horizontal that can be used on pseudo-uniform grids. That means like grids like the cube sphere or the icosahedral grid, but preserve properties of the C-grid finite difference method that they currently use on the latitude-longitude grid. So that's the kind of the challenge. And so I'm going to start by just kind of sort of saying, why is it that the C-grid works? And we've already had quite a lot of discussion about that. In particular, John was talking about it at the beginning. So a lot of the properties that we like, the local conservation of mass, the absence of spurious pressure modes, the fact that geostrophic modes are steady on the F-plane. So these are all 3 things which are kind of pretty much essential for requirements for our project, and these other things are nice as well. All of these properties of the kind of the schemes and their kind of descendants arise from discrete versions of various calculus identities that we teach to undergraduate students. So the fact that div curl is equal to 0, the curl over grad is equal to 0, and also the fact that the div perp dot perp u is the divergence of u, where grad perp is k cross grad. These are things which we teach to students, and which we can show, which we use to show all of these properties of the continuous equations, and we want to build them into the numerical scheme as well if we want to preserve them. Okay, so I'm not going to talk very much about this because John already gave an introduction, but just to say that it's mostly about where you place, in the finite difference world, it's mostly about where you place the various degrees of freedom. So for example, if you want to take a gradient, so if you've got a function that's stored in the vertices, you can take a gradient, and that gives you a velocity field where you store the normal components on the edges. And then if you then do a circulation integral around that to get the vorticity, then that will vanish. So for example, that's how we kind of build in this scheme. So John already talked about the fact that you can kind of extend this to kind of arbitrary polygons. And we've already observed that with the triangular case, there's too many pressure degrees of freedom compared to the number of velocity degrees of freedom, and that leads to inertial gravity wave modes. Some people have talked about that quite a bit. The hexagonal grid has more more than usual number of velocity degrees of freedom compared to the pressure, and that leads to spurious Rossby modes that exist, although John showed that maybe we don't care about those. And it's the quadrilateral case that we would like to be able to use, because it's got this perfect balance, but then you kind of lose this kind of, then this orthogonality property causes problems on that grid. So, so my kind of approach, my objectives are to kind of take a finite element extension of this approach that's just been talked about in the last 2 talks. And there's a few reasons for doing that. So one is that you can use higher order discretizations, and that might allow us to reduce grid imprinting. A second thing is that the extra flexibility means you can relax the orthogonality constraint. There's no constraint on, you can use arbitrary kind of meshes as well as within the framework. And you can also tinker with the degree of freedom ratio between velocity and pressure, and you can avoid spurious mode branches. Okay, so all we need to do is take these kind of mimetic properties that were in the finite difference method and just kind of port them to the finite element method. So let's remember what properties we need. So we need to build in the fact that the div of the grad perp of a stream function is equal to 0. We need to have the property that if you take a gradient and then you compute the vorticity of that gradient, then you also get 0. And the property that you need for the steady geostrophic modes and for the potential vorticity conservation is actually this property, which is that if you take a velocity field, then you take a perp, as you'd need to do for Coriolis, and then you take the and then you compute the vorticity. So you take the grad perp dot of that thing, then that's the same as the divergence of u. So that's the property that you actually require to have steady geostrophic modes on the F-plane, which is a property that we need. Okay, so in this mimetic finite difference world that Thomas and John were just talking about, then so the idea is that feature 1 is obtained on a primal grid, and there's a dual grid where you apply feature 2, and then feature 3 involves mapping between the primal and the dual grid. So the key difference is that in general, in the finite element approach, we don't have a dual grid, so we have to do something slightly different. Although watch this space for kind of future developments I'll talk about a bit. So in the finite element world, what we do is we circumvent this problem by we build finite element functions that automatically satisfy 1 by kind of construction, and then we can get 2 by integration by parts in the kind of finite element framework, and then we can use the finite element projection for 3. So we can get all of these 3 things within a kind of very kind of standard kind of familiar kind of finite element type operations. Okay, so how do we build in property 1? Well, what you do is you choose your various spaces very carefully. So there's this space here is where the pressure lives and the divergence. This space is where the velocity lives. And you should choose your velocity space so that if you take a divergence of a velocity function that you allowed in your finite element expansion, then you get something that's allowed in your pressure expansion. And similarly, there's a third space, which is where your vorticity lives and your stream function. And you should choose this space so that if you take the grad perp of a stream function, you get a velocity field, then you get a function which is in your expansion for the velocity field. So what happens is that, and so that means that you can take a grad perp and then take a divergence, and you haven't done any approximation, and therefore the identity still holds. And so the main thing you notice here is that you're going to lose continuity at the element boundary. So you've got a fully continuous finite element function here. Take the grad perp, you're not going to have tangential components being continuous anymore, but you will have continuous normals. Then take a divergence, and you'll have a completely discontinuous function at the end there. So some quick examples. So one example that I like is you can have quadratic. So these are functions shown on a single triangle. Of course, you've got to glue them all together over the whole mesh. So quadratic functions that are continuous, that I'm right. This is one way to represent the vorticity. Then you can take the curl, and what you get is linear functions with continuous normal components, which is called the BDM1 space. And then you can take a divergence. Then you get piecewise constant functions. And there's another. So this is another example that this is the one I'm actually using. I don't have much time to explain why right now. Okay, so how do we get the other 2 properties? So let's talk about the Coriolis force first. So in the finite difference method, you spend a lot of time trying to get the reconstruction of the Coriolis correct. So the point here in finite element land is that if you've got a velocity, it's got continuous normals but not continuous tangents, and then you perp it to do the Coriolis, and then you get something that's got continuous tangents and not continuous normals. So we can't just write down an equation like this, ut plus f u perp, etc. So what we have to do is we have to take our u perp and project it back into the velocity space again. And so I define this projection operator here. And so the idea is that this, for any admissible velocity test function w, then the dot product of w with the projection with u perp is equal to just the integral of w u perp, and this has to be true for all w. So this is just the standard finite element projection. So finite element, the idea is that if you have a term which you can't evaluate in the original space, then you project it back again, and that's what we do for the Coriolis. So the Coriolis reconstruction is very simply defined like that. So just remember, so now I've got these projections that take us, so project things into the velocity space, into the pressure space, pi v, and into the vorticity space, pi e. So these are the various projections I want to use. Okay, so I'll come back to showing why that gives us the third property in a minute. Meanwhile, we want to take gradient of functions which are over here to do the pressure gradient, but they're completely discontinuous, so we can't take the gradient naturally. So what we have to do is do a type of projection that involves an integration by parts. So I define this grad tilde operator as being that, so if you take any vector field w from this space and dot it with my grad tilde, then that's equal to minus the divergence of w times d, and this has to be true for all w. So that then defines my grad tilde operator. And then similarly, you can define a grad perp tilde operator that goes from here to here, same way, integrating by parts, and therefore avoiding the problem that you've got these loss of continuity. So the grad perp and div are exact, and the grad perp dot are numerical approximations that go the other way, as you can see from this diagram at the bottom. Okay, so let's now let's now check that gives us grad perp.grad is equal to 0, which is the property 2. So we have to do this all inside an integral. So we start with so let's take our grad perp dot grad, apply it to a discontinuous function d, and then multiply by a test function from the continuous space, because that's where this thing will live. And then we first apply the definition of grad perp tilde dot, and then so we get one integration by parts, and then we apply the definition of grad tilde, because this guy lives inside the velocity space, and then you've got a d of grad perp is equal to 0. So you get this property kind of weakly by integration by parts at each stage, and therefore grad tilde perp dot grad tilde of anything is equal to 0. So we've got property 2 by integration by parts instead of by going via a dual mesh. Okay, let's so the third property, which is required for the steady geostrophic mode, is that grad perp dot u perp is equal to divergence of u. And the discrete version of this is that if you start with u, and then you perp it, and then you project it back in, and then you do the grad tilde perp, so this is my weak approximation of the vorticity operator, then that's actually equal to taking the divergence and then projecting into the vorticity space. So that's the magic identity. I could show you the quick proof, but I don't really have time, but it just involves applying the definitions at each stage, and you get from one to the other with an arbitrary test function, gamma. Okay, so that's all of my three operations. So let's now write down some equations. So here, let's first of all look at the linear rotating shallow water equation. So our goal here is to prove that if you have the divergence being equal to 0, then the vorticity is steady, which is what you need to show that geostrophic modes are exactly steady. So here's my model equations that I want to approximate. And now to get to the finite element discretization, I just have to put in these projections and grad tildes every time I can't actually evaluate an operator. So I'm allowed to take a divergence, so that just stays the same here. So the D equation is exactly the same. Just now we're restricted to this pressure space for D. I've got to replace this grad by grad tilde, which it's got from integrating the divergence by parts, and I've got to project my u perp back into the velocity space with this projection. Okay, so if we're on the F plane, then we can now just hit this whole thing with my vorticity operator. So I just apply this vorticity operator. So if I hit so let's concentrate on this term first. So I've hit this with the vorticity operator. We already know that that's 0 from property 2. And then here we've got, I've just hit this term with my vorticity operator. And now I can use my magic identity number 3 and rewrite this as the projection of the divergence of u into the vorticity space. And so if the velocity field is divergence free, then this term vanishes as well, and therefore the vorticity is steady. So that's proof of steady geostrophic modes done on one slide by adding a projection and a tilde onto the discretization. So we have a scheme with steady geostrophic modes built in, which is one of our requirements. Okay, let's have a look at how we do the nonlinear shallow water equations. So it's exactly the same idea as for the C-grid. So we start from this vector invariant form, in which you write du dt plus, and the advection term is split up into two parts. And so you've got this vorticity flux perp, this q perp here, and then grad gd plus kinetic energy, and then this is the nonlinear D equation. Okay, so what we do now is we can just rewrite all of this. So this so the q is going to be in the velocity space, so it's perp, so we have to project it back in. We're not allowed to write a gradient, so we have to write a grad tilde. This guy here is not going to be living in the pressure space, so I have to project it into the pressure space before evaluating the gradient. And ud is not in the, I can't take a divergence of ud because d is continuous, so I first project ud back into the velocity space and then take the divergence. And then my goal is to work out what is the correct value of this q, which is going to be the vorticity flux. So I want to choose q such that if we diagnose a potential vorticity, then the potential vorticity is conserved. That's the goal. Okay, so let's get the vorticity equation. So for the vorticity equation, I now just hit this with my vorticity operator, grad tilde perp dot. So here's my d by dt of vorticity. This is the vorticity hitting the Coriolis term, and then this stuff all vanishes for the same reason, which is my property 2 holds. So that's all gone. And now I want to introduce a potential vorticity. So potential vorticity is the vorticity plus f divided by d. But the vorticity, I want it to live in the potential vorticity I want it to live in the vorticity space, whereas d lives in the pressure space. So I just kind of define this implicitly. So I say the projection of q times d into the vorticity space is equal to the vorticity plus the projection of F. And this implicitly defines Q. So I have to solve a little equation to get Q out. So that gives me the potential vorticity. And then I can, because I've got a vorticity here, this is independent of time, I can substitute this into here and then replace this with this guy. And then I get d by dt of pi e qd. And now here I've used my magic property 3. So this becomes just the divergence of Q projected back into the vorticity space again. So that's my potential vorticity equation. And now I can use this to work out what Q is supposed to be. So here's my potential vorticity equation. And then so Q should be equal to, there's a missing Q here, sorry, the potential vorticity times my mass flux, which is the projection of UD back into S. So let's substitute that in. So now, to get the div QUD term, I take UD, project it into S, multiply by Q, divergence, and then project that into E. And you can just check by calculation that if Q is a constant, then you can take the Q out of here, and then you just recover the D equation here, and therefore that vanishes, and that implies that dq dt is equal to 0. So that means that the potential vorticity equation is consistent with the mass equation in the sense that if the potential vorticity is constant, then it stays constant for all times, which is a property that you want. Okay, so I don't have time because I've got 3 minutes left, so I won't go through all these calculations, but you can derive conservation of mass, you can derive conservation of potential vorticity by just applying the various rules, you can derive conservation of entropy by the same kind of rules substituted in, and it's a bit of a longer calculation, but you can also derive conservation of energy from the same calculation. So, and these things simply come from writing down what all these quantities are, taking the time derivative, and then substituting in, and then just using these various properties that I showed you. No time for that because I want to quickly discuss some a couple of things. So one is to talk about how to stabilize the potential vorticity advection, and the other thing is I want to show you a few numerical results to prove that I am actually doing something real. So let's just kind of slow down a little bit. So let's think about where potential vorticity is being stored. So we've got this nice DG space or finite volume space that's really good for doing advection. That's what kind of DG was kind of invented for. So that's really good for the mass. The problem is that the potential vorticity lives in this continuous finite element space, and continuous finite element advection is not stable because it's high order. There's no, and so therefore you get lots of oscillations, and it shouldn't be used for advection. And so I was a bit worried about this to begin with because I was thinking, oh well, I want my potential vorticity to live over in the DG space where I can stabilize it. But I realized I don't really need rigorous bounds to the potential vorticity. I just need the advection to be stable and not too oscillatory, so that I can kind of keep control over the divergence-free components of U. And so what you can do is you can just introduce an extra dissipative fluxes, which can also be written in this framework. So for example, you can just stick in a Laplacian diffusion. You can use the anticipated potential vorticity method, which is being used as well as to stabilize the PV in the MPAS setup. But I actually like to use streamline upwind Petrov-Galerkin, which is a standard way to kind of stabilize finite element schemes. But it turned out it can be incorporated into this framework as well, and it amounts to a modification of the potential vorticity flux related to the residual. And the nice thing about this scheme is it stabilizes the advection and it remains high order convergent. So that's what I'm using. But there's quite a lot of research to be done in what are the kind of the exact good things to do here. So I put this together. We've got 1 minute. Red light. So I put all this together in a sort of implicit setup that's quite similar to the one that John described. I pretty much just copied what he did. So it's got this kind of incremental pseudo-Newton formulation. Most of the things, these things are just kind of details. It doesn't really matter. It's not really, you're not really nailed down to these things. But I used hybridization, which I don't have time to describe, to do the Helmholtz equation. It means I've got an implicit Coriolis built in there. I do some DG advection for the mass, and I use this stabilization for the PV. So let's quickly have a look at a couple of test cases because I've got now 0 minutes left. So I've really, to be honest, only just got this code working a few weeks ago. So I'm working through these standard test sets now. So this is the solid rotation test case, which is utterly trivial if you have a latitude-longitude grid. but does tell you something if you have a icosahedral grid, as I've been using here. So what I do observe is second order convergence in L infinity and L2 and all of the quantities, except for reasons I don't completely understand, I'm getting slightly slower convergence in L infinity. It seems to be somewhere between first and second order. I haven't quite sorted out what's going on there yet. And hot off the press, thanks to Hilary for helping me with some of the parameters and producing this plot here. So this is from the spectral reference solution, and this is my this is the height field for this flow of the Manta case after 15 days, and this is what my code produces. So it's pretty similar. I haven't quite tracked down why this contours emerge here. There might be a bit too much dissipation there, but anyway, the thing is producing correct results in some sense. And here are some plots of the potential vorticity evolution over 50 days. So you've got 0 days. So there's where the mountain is, and the z-axis is pointing up that way. So it's the North Pole sticking up out there. I just chose it as an interesting angle because you can see some nice filaments. So what happens? So this is potential vorticity rather than vorticity, and you can see what's happening is a kind of fine scale kind of filaments are forming after kind of 50 days, and there's so you can see that the stable. This is just to show you that the stabilization is working. So I'm not getting kind of unstable advection of the PD. So the next thing to do is to kind of compare with some of the other cases of whether this is even close to being the right thing. Okay, so I just Todd stood up, so I'll give some quick kind of summary and kind of outlook. So what I've done is I've taken the kind of hermetic scheme that was extended to kind of arbitrary polygons in Trisk and kind of put it into a kind of finite element kind of framework. And I think the important thing to remember about it is that I've used different spaces for the stream function, the velocity and the pressure, where this grad perp dot and the divergence operators are designed to map from one to the other. That's crucial to the whole thing. And it allows you to go to higher order, have non-orthogonal meshes, and to tinker with the degree of freedom count. So we're getting towards this end of phase one with this gung-ho project, so we need to really get these test cases comparisons done. There is a future abstract for a talk at the next workshop where John is going to talk about a primal dual version of this, where we've kind of sort of merged the two ideas together. So so you can actually use the good things about the finite element in terms of the consistency and so on, but still have these primal and dual grids. And I'm currently banging my head about how to extend this to the 3D case as well. And here's a few papers. So this is, John already talked about that one. This is the paper where I first started talking about these kind of using these kind of mixed finite element methods for numerical weather projection. And we've got another submitted paper which is on the archive, which discusses the kind of the nonlinear formulation of both this formulation and the primal dual one, which is available on the archive, and probably someone in this room is reviewing it. So yeah, so that's everything.
Questions for Colin?
Your projection operator you use for the velocities to be continuous along the elements edges.
Yes.
How expensive is this important?
Well, it's a mass matrix, so it's a good, so it is. So the thing I would say about the mass matrix is the number of iterations required to get to a given residual is independent of the resolution. So it's a very well conditioned matrix compared to elliptic problems and so on.
Actually,
so you, like the last slide you mentioned, you're looking at 3D PV conversation.
Yeah.
Is that for hydrostatic or non-hydrostatic or both?
Yeah, so our target model is non-hydrostatic compressible, so the whole 9 yards. I've actually already worked out how to do it. If you don't mind locating your temperature with the potential vorticity, but you really want to have a Lorentz, Charney-Phillips grid, where you locate it with the W to avoid the spurious mode, and that is the. I've got pages and pages in my notebook of kind of Ds and stars and things where it's not quite working, but that's the.
Yeah, it sounds like a mess.
That's the thing I'm trying to do.
Jürgen?
Your polynomial spaces are relatively low in degree. So if someone has the ambition, like the spectral elements, to use relatively high, say a minimum of degree 3, would you have to offer also these properties? Could you have
Yes, so
the choices which you did?
Yes.
Higher spaces as
Yes,
well?
so I just show those low order ones because it's easier to digest. So in particular on the quadrilaterals, then there's a you can use the Ravier-Thomas of any order, so 1, 2, 3, 4, 5, 6, 7, etc. On triangles, the main thing is that you want to use these properties, plus you also want to have a nice balance of degrees of freedom. So on triangles, I haven't found a higher order one yet, which has the nice balance of pressure and velocity degrees of freedom, but I've got the rules of how to construct it. So yes, nothing here prohibits high order.
Yes, you shortly talked about entropy computation. Is this an issue which you want to take over to the 3D equations, and which physical reasoning is behind this?
Okay, so let's go back there. This is just built in, so you can't avoid having this. So I had to, the dissipation that I was putting in here to stabilize the PV was actually dissipating entropy whilst conserving energy, which is something that's kind of relevant to 2D. So for 3D, I think it would be more complicated how you want to dissipate it. I usually take the view that if the formulas give you something that's conserved, then you know that if you put some damping in, then you're just taking out that thing rather than because you believe that should be conserved in the 3D model.
Well, I would just say if your scheme is conserving energy and it can conserve potential entropy, that is something new. That is something that the finite volume schemes that maybe this was stimulated from can't do. They can do one or the other, but they can't do both. You have to go back to Arakawa 81, and he actually changed the PDE to get that. So if that's the case, that is something. Great. Let's thank Colin again.
Yep.